because this just came out of the laundry. And every time I pull a new mask out of the laundry, it's basically a game of guess how much Earl fur, cat fur is on the inside of the mask. I do not enjoy it. All right, and it looks like it's starting, so I will cancel out. So now we're going to talk about problem solving, and we're going to start by looking at the Gestaltist approach to problem solving. So the last time that we talked about the Gestaltists was way back in chapter 2 when we talked about visual perception. But this wasn't the only thing that the Gestaltists actually did. They were interested in productive thinking and finding creative solutions to problems. So when we talk about problem solving, I want to spend a little bit of time talking about some of the ways that we often find ourselves stuck when we're trying to solve a problem. And part of the reason that we sometimes get stuck with problem solving is because we try to solve problems based on things that have worked for us in the past. And one of the things that is very clear is that sometimes that will work. Using your past experience to help you solve a problem can be a very good approach. It's certainly better than throwing spaghetti at the wall and seeing what sticks. But sometimes we get stuck with problem solving because we are stuck in a past mindset, and we need to think about the problem in a new way. So we need to be able to think about the problem in a new way and restructure it in a new way. And this can include, the Gestaltists really emphasize that restructuring the problem is what's really important. And this can include such things as insight, which we'll talk about. We'll talk about incubation. So how many of you have had this happen where you've spent a lot of time trying to find a solution to a problem and nothing's really coming to you? And then all of a sudden, if you take a break or you go for a walk, or in my case, this is what always happens with me, I get in the shower and all of a sudden the solution magically appears. This is what is known as incubation. So incubation can be part of that. And then also representational change. So I know that some of you have seen this in general psychology. I show this all the time. Do not spoil it for anybody that hasn't seen the problem yet. Ashley, since you're visiting, you're also more than welcome to try this problem. So this is a pretty famous problem where we have 6 matchsticks. And what you have to do is basically arrange the matchsticks in such a way that you form 4 equilateral triangles. That means that the sides have to all be an equal length. So does anybody who hasn't seen this before, and I know that you two have seen this before, but maybe you don't remember. It's okay if you don't, but does anybody have a potential solution for the problem? If you've seen this before and you know the answer, try not to spoil it. Okay. Is anybody struggling to kind of figure this out? Now, I will tell you that occasionally somebody tells me that the solution to the problem is this. So you take one matchstick, one matchstick, one matchstick, one matchstick, and then you put the 2 in the middle. The problem with that is that these 2 that are on the diagonal, they'd have to be longer than everything else because the hypotenuse would have to be longer than the 2 sides. So that's not the correct answer in this case. But here's what we find. Let me take a look and see if anybody on the chat has an idea. I don't think so. Okay, so here's the problem. The matchsticks are laying flat, as you can see. But I never told you that the solution had to also be flat. Now, do you have a better idea of how to represent this answer? Did anybody get something like that? Now, for those of you that have had Gen Psych with me, you're like, oh yeah, I remember this now. So the idea is that people get stuck here because of how they're representing the problem. You see the matchsticks laying flat. You think that the solution to the problem must therefore also be flat. It turns out that's not the case. And if you're constantly stuck in this reproductive thinking, you're never going to be able to break that tie to your past experiences and look for something new. Look for a new creative solution that has been represented in a very, very different way. Now, this has also been presented in general psychology. So if you know it, don't spoil. I'm going to give you a candle, a box of tacks, and a book of matches. This is a very famous problem called the Dunker candle problem. Your goal is to attach the candle to the wall next to the table, and you can't drip wax on the table. Does anybody have a solution to this problem that has not seen this before? My examples are so good, I just use them everywhere. And while you are waiting, this lecture was brought to you today by Cherry Bubbly. I promise I'm not getting sponsored, I'm just being cute. Oh, I'm thirsty. Okay. Does anybody have an idea on how to solve this problem? I'm going to assume the Wi-Fi is crashing. Is that the fair assumption? Who knows? Ava, Ashley, have you, oh, well, now I spoiled it for you. Dang it. I was gonna see if you knew the answer, but did you come up with something like this? Robin, is that because you've seen this before?
It took me a minute to like figure it out.
Ashley, did you have any idea on how to solve it? Ava, no idea? So the idea here, and this again is a case where representing a problem in a brand new way can help us think creatively and achieve a creative solution. So we have this box of tacks, and here's where people get stuck here. They go, oh, that's a box of tacks. It must just be for tacks. And one of the things that we actually find is that if you empty that box of tacks, most people suddenly realize at that point you can use the box instead. It's not just for holding tacks. So I will tell you, I first received this problem in my cognitive psychology class in my junior year. And my solution was to take a bunch of these tacks and basically ram the candle into the wall, forgetting that the tacks, of course, are not going to be fat enough to actually hang the candle to the wall. And it doesn't do anything to stop the wax dripping. So let's talk a little bit about insight. So insight often happens because of this sudden restructuring. So I actually presented the matchstick problem to my general psych students last week. And when I said, I never said it had to be flat, for some of them, it was almost like you saw a light go off in their eyes or a light bulb popping above their head. When you have this sudden realization about how to solve a problem, this is what is referred to as insight. It is kind of described as kind of when you get a little light bulb above your head experience, when you, is that a wasp up there? I don't know what that bug is. Please don't sting, Emma. Okay. So we get this sudden realization of how to actually solve the problem. And oftentimes we're going to find, and based on the work that the Gestaltists have done, this ends up happening because you suddenly realize how to restructure or reorganize the problem and the means to the solution. As we kind of talk about in general psychology, insight is also part of the reason that we enjoy jokes. That sudden realization of getting the punchline of a joke can also be thought of as an insight experience. So here's an example. So this is a pretty famous puzzle from Kaplan and Simon in 1990, and it's called the mutilated draft board problem. So what you can see here is that we've got a checkerboard or a chessboard, and we have two squares removed. So the idea behind the mutilated draft board problem is that you want to see whether or not you can fill up this entire draft board with dominoes. So the idea basically being, is it possible to actually remove these two squares and cover the remaining 62 squares with 31 dominoes? Okay, so does anybody have a solution to this problem? So how do you think you solve this problem? Who says, yes, you can cover this with 31? Who says, no, you can't? Okay, so usually when most people do this, they start by, how many of you are currently covering all the squares with dominoes in your head? That's what most people do. And the problem with that, and your textbook actually notes this, alas, this strategy is not terribly effective because there are 758,148 possible permutations of the dominoes. There's a really easy solution here. So if we look at these squares, if I put a domino on the board, how many black squares and how many white squares is it going to cover? It's going to cover one black square. It's going to cover one white square. So every domino that I place down is going to cover one of those. Now, because of that, can you tell me which two corner colors have been removed? They're both black, right? So because they're both black, that means that there are more white squares on this board than there are black squares, which means you cannot actually cover the draft board with 31 dominoes. You can't. There are too few black squares and there are too many white squares. And that's all you really have to do to solve the problem. So when you restructure it that way, it suddenly starts to make more sense. So animals too can also use insight. So what you're looking at here, this is based on, this is based on the work of the Gestaltists. So the Gestaltists actually looked at how chimpanzees solve different types of problems. And this is a chimpanzee named Sultan. So they would put Sultan and other apes in these situations in their big cage areas. They'd always be trying to get different types of bananas. So the banana was always the reward, but the banana was always very, very hard to get. So this is largely based off of the work of Wolfgang Kohler, by the way. So the idea being that there would be a banana in the cage, and there would be two sticks. Now, each stick on its own would be too short to get the banana. So the banana is kind of hanging up in the center of the cage. Neither this stick nor this stick is large enough on its own to actually get to that banana. But what's really interesting, though, is that sometimes with little nudges or with little hints, the animals were actually capable of reaching the solution. When a researcher actually went into the cage and accidentally put the sticks together by accident, the ape suddenly realized that the sticks could be put together to make a longer stick, and thus the ape was more likely to actually reach the solution. They've also tried this with a couple of boxes to try to get a banana. And then the ape realized that he could stack the boxes to get the banana. So your book talks about this as well. So these little nudges not only work for apes, but they work for us as well. So we'll talk about, do you need me to go back, Robin? Okay. So I want to talk a little bit very quickly about this aha experience. So typically, one of the ways that you can actually measure this with insight is what is called a feeling of warmth. So a feeling of warmth is kind of like when you hide a gift for your friend and your friend is trying to find it and you're like, oh, you're getting warmer, you're getting warmer. Oh my gosh, you're hot, you're on fire. Or when you're getting away from it, well, you're colder, you're getting colder. So the idea is that people were asked, Metcalf and Weiba basically asked people while they were solving different types of problems, whether or what their feelings of warmth were like as they solved a problem. So they would have an insight problem, or they would have like a non-insight problem. So something like a math problem. So here on our x-axis, we have time. Here we have our feeling of warmth. So here's what happens in a problem that does not involve insight. Feeling of warmth progressively increases as you get closer to solving the problem. Insight problems don't work that way. Insight problems look like this. The feeling of warmth stays really low until all of a sudden they get the solution. And that feeling of warmth is occasionally enough to help people figure out that these are different types of problems and that these are using different brain areas. So people have done research with insight problems doing something called a remote associates test. So I'm actually going to give you a couple of these. And by the way, it's called the RAT for short. Okay, so this is a test that was developed back in 1962. Each RAT question presents 3 keywords that are linked by a 4th word. Okay, so I'm going to give you 3 items, and I want you to tell me a word that is connected to all 3 of them. Are you ready? Okay, cottage, Swiss, cake. What is a word that is connected to all 3 of those words? Cottage, Swiss, and cake.
Cheese.
Cheese, yes. So it's cottage cheese, Swiss cheese, and cheesecake. Here's another one. Cream, skate, and water. Ice, good job. Okay, now I'm going to make it tougher. Let's try a medium difficulty one. Peace, mind, dating. Nope. Peace, mind, and dating. Oh, let's see what we got. Yeah, you got cheese. Good job. I didn't see that. I'm sorry. Peace, mind, and dating. I'll tell you the answer in a minute, but I want to see if anybody can get it first.
How is peace spelled?
P-I-E-C-E. Okay. Anybody got it? Oh, let's see if we got it. If we don't know, are we dumb? No, this one's rated as very hard. No, the other ones I gave you were easy. This isn't a dumb or a smart thing. It's actually a test of creativity. The answer is game. So game piece, mind game, and dating game. Okay, let's try one that's medium. Flower, friend, and scout. Huh? It's girl. Nice job. So it's girl, friend, flower, girl, and girl scout. So you can kind of see where insight pops in. So with that one, did it just pop in your head and you're like, uh-huh? And you didn't really have a very sudden feeling of warmth with that, did you? Probably not. So you can find those online. If you like exercising your mind, they're a lot of fun. I actually really enjoy them a lot. Okay. Let me see if there's anything else I wanted to add with this really quick. Let's see. All right. So I will kind of mention too, when you look at brain activity with these kind of remote associates, they had to indicate whether their answer had insight or not. And they actually found, this was by research by Bowden and colleagues in 2005, the anterior superior temporal gyrus was activated only when there was insight. And additionally, they had stronger activation in the right hemisphere than in the left hemisphere. And there is some idea that that's because the right hemisphere tends to be more involved for things like creativity, a little bit. I'm not getting into that right brain, left brain stuff. So one more. Think of a single word that will go with each of these words: fence, card, or master. I like these. These are fun. Nice work. Well done. So it's fence post, postcard, and postmaster. Nicely done. So these are the brain areas that appear to be involved in insight. Generally, the right hemisphere of the brain is going to be more involved because the right hemisphere is typically more involved in the semantic relationships between words. So figuring out the relationships between the words' meaning. The anterior cingulate cortex also does tend to be involved. This area is really important for conflict, and not like conflict like, oh, me and my friends are fighting, or me and my sister are fighting, not that kind of conflict, but cognitive conflict. So for example, if you're a freshman here and you can't say the word duck, and you really want to say the word duck, but you know you can't, the anterior cingulate cortex is going to be very, very highly involved because it's monitoring a conflict between what you want to say and what you shouldn't say. And it turns out that the anterior cingulate cortex does play a role here as well. It's monitoring the conflict between the old thought processes that are typically inefficient and not very helpful, and the new thought processes that we have. All right. So this does kind of suggest that insight is something that's kind of special. So how can we help insight to happen? So we know that hints often help. Even really subtle hints can really work for us. It doesn't take much. So we're going to talk about another famous problem called the pendulum problem. So this was originally developed by Meyer in 1931. And the idea behind this problem is that you go into a room, you have various objects that are nearby, including things like a chest and pliers. And then you've got two strings that are hanging from the ceiling. And your job is to tie the two strings together. Now that doesn't sound like a lot until you realize that the strings are so far apart that you're not going to be able to reach out and tie them with both of your hands. So here's what the problem kind of looks like. So the idea here is that you've got these two strings. You've got a variety of other items in the room. You cannot tie these together using your own hands. So does anybody know what the solution might be here?
Would you move?
Robin, you want to give it a shot?
Yeah, we can use the chair and tie them together. I use the back of the chair and like put the chair like just a leg in the back.
Well, the original problem doesn't have a chair. The original problem doesn't have a chair, and unfortunately, even with the chair, they're still going to be too far apart for you to tie them.
Would you swing
Anybody else?
Would you swing the rope so that you can stand next to the other rope and then you catch
So
it?
here's why they call it the pendulum problem. So you take the pliers, you tie it to the end, you swing it like a pendulum until it meets the other one, and then you can tie them together. Yeah, I know. I'm like, yeah, the chair seems like the easy solution too, but Meyer apparently really wanted his participants to work for it. But here's what's interesting. So researchers have, so let's get back to this idea of subtle hints. So researchers have found that the pendulum problem is solved a lot more easily. For example, if somebody brushes up against the string to make it swing. When people accidentally do that, the problem is more easily solved. Your book also talks about researchers who would occasionally make their participants trying to solve the pendulum problem do exercise breaks. And during the exercise breaks, they either did one of two things. Either they stretched their arms like I'm doing right now, or they had to swing their arms up and down. I wonder which one of these looks most like towards getting the solution of the pendulum problem. It's this one. And it turns out that when you have people have to swing their arms up and down like this, this actually leads to more people solving the problem than the people who were just stretching. So it doesn't really take much to get us to understand how to reconstruct a problem. Sometimes we just need a little hint, and it doesn't even have to be a very big one. And prior experience also plays a huge role. So going back to the candle problem, you know who doesn't really have a problem with the candle problem? Children. Children tend to have an easier time solving the candle problem than adults do. Does anybody know why that might be? Why would children have an easier time solving the candle problem than an adult would? So think about it. Well, first of all, kids are really imaginative. So I couldn't tell you how many times when I was a kid, I would grab a paper bag and I would cut out holes in the arms and the head, and I'd put it over my head, draw a circle on my chest with crayon, and I'm like, I'm a Care Bear. Like, kids do that kind of stuff. How many of you have taken something that was clearly meant to be used for something else and you decided to play pretend with it? I'd make puppets out of paper bags. I would make pillows and chairs and sheets into forts. I did all kinds of things with boxes. When you're young and you don't have a lot of experience with objects, you can see the potential uses much better than an adult who has been using boxes for holding things for a good chunk of their life. The older you get, the more experience you get with boxes being used for holding very specific things. A tack box must only be used for holding tacks. And the more time that you spend with objects in that way, the more that you have problems imagining that that box could be for anything else. And this is what's known as functional fixedness. It basically has the idea that an object only has one function, and that's the only function that it needs. You can't imagine an object being used for something else. And it actually limits us in terms of how we use an object. So it is predicted that the less prior experience you have, the less functional fixedness you will have. And it turns out that kids have a much easier time solving the candle problem than an adult does. Now we're going to try something different. So we're going to do something called the water jar problem. You don't need to write this down just yet. So not only can we get stuck in seeing the functions of objects as being very, very fixed, we can also get very, very stuck in reaching the solution of our problem. So what you're looking at, we're only going to do a couple of these. This is what's famously referred to as the water jar problem. So you have three different jars. You have jar A, B, and C. So for each jar, you have the capacity of each jar listed. And then you have a goal. So using different combinations of these three jars and by adding or subtracting, you need to reach this particular goal. So here's an example. So you may obtain the goal amount by adding or subtracting the quantities listed in A, B, and C. So with our first one, we have a goal of 100. Jar A holds 24, jar B holds 130, and jar C holds 3. How did we get to 100? So what do we need to do to get to 100 on problem 1? Yeah.
Does A, B, and C need it each have 100 in it?
No.
Does it either jar needs 100?
You're thinking kind of too much. So we just need to make sure that we have the specified amount of liquid in the jar, even if it's not, or let's just imagine we have a bucket that we put those, you're overthinking it. Okay, I can give you the answer to the first problem. Would you like me to? So the idea behind the first one is that we get a jar of B, we fill it up, so it's 130, and then we remove A and then C twice. So we do 130 minus 24 minus 6 equaling 100. Does that make sense? Okay, now what would we do for problem number 2? Here, A is listed as 9, B is listed as 44, and C is listed as 7, and our goal is 21. Now, how many of you noticed the same solution that I did last time works here too? Okay, because it does. 44 minus 9 minus 14, so 7 twice is 21. And the same is true for number 3, and number 4, and number 5, and number 6, and number 7. Here's the problem though. That's really inefficient, isn't it? Like when most people do this problem and they realize that the solution to the first problem is fill up B, remove A, and then C twice, they start applying that to every single problem in the set. But you don't have to do that. For example, C is 21, or C is 7, and your goal is 21. You could fill up C 3 times, and that looks so much easier. Here, we've got 29. This one could be a little bit trickier, but you could do A with 21 and then add C twice. You don't even have to involve B at all. But once you get used to solving a problem a certain way, you tend to apply the same set over and over again, even if it's inefficient. This fill up B, remove A, and C twice is a lot of work. And there are other ways to get to the problem here. So what does this mean? This means that our previous experience using a strategy influences how we solve similar problems, even if it's inappropriate or not as optimal as others are. So I want to talk about another way that we can engage in problem solving, especially related to insight and how it works. And this was originally developed by Olson in 1992, and this is what's called representational change theory. And so here are kind of the major assumptions. So when it comes to solving insight problems like the ones that we've been talking about today, part of the reason that we end up having difficulty solving the problem is because we get stuck representing the problem a certain way. So here's kind of how the theory works. So first of all, the problem representation and how we are choosing to represent the problem is basically functioning as a retrieval queue. And retrieval in this case is going to involve spreading activation. So if we are representing the problem a certain way, activation is going to spread to other problems with similar representations that we've tried to solve before. But the block is that the way that we are currently representing the problem is what is preventing us from retrieving the solution. So changing our representation ends up breaking that block. And that can include a couple of different things. This can include what Olson refers to as relaxing constraints. So basically getting rid of your ideas of what is permissible and what is not permissible. So for example, in the matchstick problem, one of your constraints could be that the problem should be two-dimensional. You can go ahead and relax that constraint and that will help break the block. You can also do what is called elaboration. You can add new information to help you solve the problem. Another thing that you can do is re-encoding. You can reinterpret certain aspects of the problem that are different from how you did it at first. So you can change your representation in a variety of different ways. And one other way that you can actually break a block is by incubation. And this is when you actually solve a problem by ignoring it for some time. Now, here's what's really critical before you start getting on me telling me about, well, if that means that I have a problem, that means I can just walk away from it and it'll magically solve itself. That is not how this works. You do actually have to do some preparation. So incubation is a really interesting way to do this. So you do have to have prep time. Prep time is absolutely critical here. So the idea being that your subconscious mind is working toward the solution. Now, this was back in 1926, and well, frankly, some of y'all know how I feel about talk about the subconscious. When people start talking about the subconscious, I start feeling kind of squeaky. I'm like, we aren't talking about Freud again, are we? Because I don't know if I can handle that in this class. But the idea being that your mind is working toward the solution. You have fed it the information that it needs. And your mind is continuing to work on it through some of these automatic processes. And CO and Omerod actually did a meta-analysis back in 2009, and they actually found that walking away from a problem for some time actually did lead to a small significant effect of being able to solve the problem. So incubation can work. But here's what's important. First of all, prep time is critical. Just like you can't learn through osmosis, you cannot expect to solve the problem if you haven't actually done any work on it yet. So prep time is critical. Additionally, this tends to work much better for creative problems that end up having multiple types of possible solutions. So we're talking about creative problems. So one of the ways that this actually kind of happened to me when I was working on my doctoral dissertation, I did I basically was able to replicate and extend somebody else's research. And I actually presented my work to this person, and he said, those findings are really good. I basically had all of the possible answers mapped out on a grid. And he goes, but how do you know they're not just getting locked into a certain grid response? And I'm like, oh, that's a really good point. And I spent weeks trying to figure out how to change it, how I could make sure that the results that we were getting were real. And then finally, after spending many, many days on this problem, I got in the shower and it hit me. I could change the grid every trial and rotate the grid so that people weren't getting locked in on a specific spatial location. So there are probably many ways that I could have solved this problem, but incubation helps. So sleeping on a problem can largely help. So what processes are involved in incubation? Herb Simon actually talks about this a little bit in 1966. And basically what he noted is that for this to work, you have to forget your old strategy. Incubation works the way it does because you forget some things. You forget strategy information. And that incubation is critical because if you held on to that strategy information, you'd still be stuck in your old ways of thinking, trying to reach a solution. So after incubation, after you've forgotten the strategy information, you can adopt a new one. And this is kind of related to interference. So in the remote associates test, researchers or participants either got clues that emphasized the differences between items, or they got no clues. So they'd get something like tank, hill, and secret. And then they would be given a clue that emphasized the differences between them. And then after an incubation period, they were asked to basically come back and try to solve the problem. And they found that the folks that had gotten the misleading cues had an incubation effect because they had to think about the different items, and then they had to forget about emphasizing their differences with incubation before they could get the answer to this example. What is the answer, by the way? It's top. Tank top, hill top, top secret. All right, so I'm going to go ahead and stop here. We're going to continue talking about different types of problem solving, and we're going to talk about analogical reasoning. Next time, we're going to talk about the famous X-ray problem, and I'm really looking forward to that. We'll talk about expertise and expert performance, and I will see you next time. Hope you have a good day.